I want to talk about gas mixtures. So we've talked about individual gases and how they relate to the gas laws. So those are typically talking about one gas itself and how changing the variables will change the gas, or how we can find the individual variables for a specific sample of gas. Now we want to talk about two or more gases that are forming a mixture. When two or more gases are placed in a container, each gas behaves as though it occupies the container alone, so it doesn't even acknowledge the other gas present. And this makes sense with what we know about gases not having intermolecular forces. Gases are so far apart from each other, the individual molecules are so far apart that they don't have intermolecular forces. So they don't have intermolecular forces between themselves, two gas molecules of the same type, but then they also don't have intermolecular forces between two gas particles of different types. So let's consider a sample of 1 mole of nitrogen gas in a 5.0 liter container at 0 degrees Celsius. We can plug that into our PV equals nRT equation and solve for the pressure of that gas in that container, and we can see that it comes out to 4.48 atm. We can then add 1 mole of oxygen gas to the same container. It would be under the same conditions and therefore would exert an additional 4.48 atms of pressure on the container. There's still 1 mole of it. It's in the same container which has the same volume, and they're both at 0 degrees Celsius. So the individual pressures of each compound is referred to as the partial pressure. So because they're mixed together, the pressure is made up of the pressure of one type of gas as well as the pressure of the other type of gas. So the total pressure of the mixture is the sum of those partial pressures. So the pressure of the nitrogen gas plus the pressure of the oxygen gas. So we can add those up and we can see that the total pressure of the entire container with nitrogen and oxygen gas both in there is equal to 8.96 atms, which is the addition of 4.48 to 4.48. So we took the individual partial pressures and added them up. We call this Dalton's law of partial pressures, and this states that the total pressure exerted by a gas mixture is the sum of the partial pressures exerted by each component of the mixture. So we have an equation here, P total, which is the total pressure, equals the sum, okay, this is a sum sign for those who don't know, of the individual partial pressures. So if we had a mixture of water, HCl, CH4, and H2 all in the same container, the total pressure would be equal to the pressure of the water plus the pressure of the HCl plus the pressure of the methane plus the pressure of H2. If I were to add more gas to that container, then I would increase the total pressure because its partial pressure would add to that sum overall. So, to reiterate, each component of a gas mixture exerts a pressure independent of the other components. The total pressure is the sum of the partial pressures, which is what this is showing here. You have these purple ones, which are exerting, a quarter of the amount on here. And then you have the yellow ones that are exerting about half on there as well. So when you combine them together, their pressures combine to about 3/4. of the total there. So let's practice this. Here, a 5-liter vessel contains 0.041 moles of helium, 0.21 moles of neon, and 0.0922 moles of argon gases, all at 25 degrees Celsius. Calculate the partial pressures for each component in the container and the total pressure of the vessel. So what we're going to do here is similar to what we saw with nitrogen and oxygen gas in our previous examples, where we want to solve for pressure using nRT over V. I just rearranged our PV equals nRT equation to solve for pressure. Except each n is going to vary for each of these calculations. So let's start with helium. The pressure of helium is equal to the mole value, which is 0.041, times R. Let's do our partial pressures. It doesn't tell us a unit, so let's choose ATM. I just really personally like ATM. It's my favorite pressure unit. So an R value for that is 8.08206 liters ATM per mole Kelvin. Okay, so we'll do ATMs for our pressures here, 0.08206 times the temperature, which is going to be 25 plus 273. Okay, so that's 298.15. And then we'll divide by the total volume, which is 5 liters. So let's do that. 0.041 times 0.08206 times, what's 25? That's 298, I'll just plug it in, plus 273.15, which we then divide by 5. Okay, so we get a pressure of helium of 0.20062 ATM. I'm going to leave a few extra decimal places just so that when we add for the total pressure, we have all those decimal places. But since we also asked for the individual partial pressures for sig figs, this will be 0.200 ATM. Okay, so then we have the pressure of neon. So it's the same setup, except now we're going to swap out 0.041 for 0.121. But the R is the same, and the T is the same. 25 plus 273 is 298, and the volume is the same. So we get 0.121 times 0.08206 times 298.15 divided by 5. And we get 0.59208 ATM. With sig figs, this becomes 0.592 ATM. And our last one is argon gas. So we have the pressure of argon is equal to the mole value, which is 0.0922 times everything's the same. Okay, so we get 0. Times 0.08206 times 298.15 divided by 5 for the volume. So that's 0.451157 ATM. With sig figs, 0.451 ATM. Okay, so those are the individual partial pressures for this problem. Now we want to take all of those individual partial pressures, add them up to find the total pressure. So we're going to take 0.20062 plus 0.59208 plus 0.451157, and we get 0.20062 59208 451157. We get a total pressure with 3 sig figs of 1.24 atm as the total. Okay, let's do another one. Determine the partial pressures and total pressure in a 2.50 liter vessel containing the following mixture of gases at 15.8, that should be a degrees Celsius. We have 0.0194 moles of helium, 0.0411 moles of hydrogen, and 0.169 moles of neon. So this is very similar to our previous problem, so let's get our R up there for you to have, 0.08206 liters atm Kelvin. So what I want you to do now is pause this video and try this problem independently to find both the partial pressures and the total pressures of this sample of gas. The setup is exactly the same as we saw in our previous problems. So we just choose each variable. Let's do helium first. And we just plug in their mole value, 0.0194 times R times the temperature, which would be 15.8 plus 273.15 to get 288.95 Kelvin, divide by the volume of 2.50 liters. So we just plug that in, 0.0194 times 0.08206 times 288.95. We get, and divide that by 2.5, there we go. 0.183999 to ATM there. Okay, next up is hydrogen. All we're changing is the mole value because that's the only thing that changes in all of our sample, but everything else is the same. Okay, so we get 0.0411 times 0.08206 times 288.95, all divided by 2.5 liters. So that is 0.389813 atm. Next up, we have the pressure of neon. So same setup, just a different mole value. Okay. (169) times R times the temperature divided by the volume So we get 1.60288. Okay, so let's see, we would have what? 3 sig figs for these, so 0.184 for our individual partial pressure, 0.390, and 1.60. Then to find our total, we're just going to take those individual ones and add them up. 18399 plus 0.389813 and 1.60288 to get 2.1718 with sig figs. And that is our total. Okay, let's see what's our next one. Determine the number of moles of each gas in a mixture of methane and C2H6 in a 2-liter vessel at 25 degrees Celsius and 1.5 atm when the partial pressures of CH4 is 0.39 atm. So let's think about this problem. We have PV equals nRT. We want to solve for N now instead of P. So we're going to say that N is equal to PV over RT. So we need to have the individual partial pressures for each component. We're given the total pressure, and we're given the partial pressure of CH4, but what we don't know is the partial pressure of C2H6. So what I want you to do is pause your video and think of how you would find that partial pressure of C2H6 given that you have the total pressure and the partial pressure of CH4. Then once you find that partial pressure, you can now calculate the number of moles for both CH4 and C2H6. So try that. Pause your video and try that now. So remember that the total pressure will be equal to the pressure of CH4 plus the pressure of C2H6. So since we know the total pressure is 1.50, and we know the pressure of CH4 is 0.39, we can solve for the pressure of C2H6. So we just take 1.5 and subtract off 0.39 to get the pressure of C2H6 to be 1.11 atm. So now that we have the pressures, we can solve for the number of moles for each of these. So the number of moles for CH4 is equal to its pressure, which is 0.39, times the total volume of 2, divided by R, which in this case is 0.08206, and the temperature, which is 25 plus 273, 298.15 Kelvin. So we get 0.39 times 2 divided by 0.08206 times 298.15. So the number of moles of CH4 is equal to 0.0318 with 3.919 with sig figs. There we go. We can do the same for C2H6, so we have N of C2H6, and its pressure was 1.11 atm, but everything else is the same. The volume's the same, the R is the same, and the T is the same. So now it's just plugging it in. 1.11 times 2 divided by 0.08206 times 298.15. And we get number of moles of C2H6 to be 0.0907. And those are the final answers for that problem. Now let's take this one step further and start discussing mole fractions. The relative amount of the components in a gas mixture can be specified using mole fractions. So here's the expression for a mole fraction. This is chi, Greek letter chi, and it is the mole fraction. Just saying that's just how we represent mole fractions. And it's equal to the moles of a certain component, N sub I, divided by the total moles in the sample. So it's like a part over a whole in our gas mixture. So if I have 4 moles of gas, and I know 1 mole is made up of hydrogen gas, 2 moles is neon, and 1 mole is argon, well, we could find that there is 1 over 4 for a fraction of hydrogen, 2 over 4 for a fraction of neon, and 1 over 4 for a fraction of argon. We could simplify 2 over 4 to 1/2, that's totally fine. Okay, it's just the part over the whole. There are a few things to remember about mole fractions. The mole fraction of a mixture component is always less than 1, right? It can't be more. You can't have more of the gas, of a specific type of gas, than the total gas in the sample. That wouldn't make sense. Okay? I can't have 4 moles of gas and 6 moles of those being hydrogen. That wouldn't add up correctly. So it'll always be less than 1. So here we have 0.25, 0.25, and 0.5. The next thing is that the sum of the mole fractions for all components of a mixture is always 1. So in our example, we have 0.5 plus 0.25 plus 0.25 plus 0.5, which all equals 1. And the final thing to remember about mole fractions is that they are dimensionless. Okay, we have 1 mole divided by 4 moles. Our units of moles will cancel on the top and the bottom, meaning that this is totally dimensionless, also known as unitless. It's another way of saying unitless. Dimensionless and unitless are the same thing. Okay, so let's use some mole fractions. We can relate the number of moles and the pressure because we can say that in a mixture, the number of moles and the pressure at which that sample exerts on the overall container are proportional to each other as long as the temperature is held constant and the volume remains unchanged. So we could also have a pressure fraction. So here's our expression for mole fractions here, but instead of Ni and P and N total, we have Pi and P total. Okay, so your pressures can have a fraction in the same way that the overall moles do. So like we saw before, we had 0.39 atm of methane over the total 1.50 atm overall. That would be a pressure fraction. The other one came from the 1.11 from the C2H6 over the total. Okay, so we can think of mole fractions and pressure fractions as the same thing. If we know the specific fraction, we can then multiply it by the total value and get the individual value back, right? Because the chi, I'm going to use it for pressure because we have it here, I have P sub I over P total. If I multiply it by P total, I can get P sub I. So if I don't know how the mole fraction was calculated, okay, then I can use that to find the individual piece. On the other hand, if I know the mole fraction for my pressures and I wanted to find the individual amounts of moles, I could do that as well. So let's look at how we can use these. I have a few practice problems that explore both finding mole fractions as well as how we can apply that to find the individual components as well. So, what is the mole fraction of O2 in a mixture of 0.756 moles of nitrogen, 0.189 moles of oxygen, and 0.0132 moles of carbon dioxide? Well, I want to find N sub I of oxygen, so that's what we're looking for. So we need to find the N total first and then divide. I should say this wouldn't be the N sub I. I want to find the chi. There we go. That's a better representation. I want to find the mole fraction of oxygen. So what we need to do, we need to calculate N total first. So we need to add up all of those mole values. 0.756 plus 0.189 plus 0.0132. 0.756 plus 0.189 plus 0.0132. So our N total is 0.9582 moles. If we want to find the mole fraction of specifically oxygen, we need to take the N sub I of oxygen, which is this guy, which I'll now label correctly with N sub I, okay, and we want to find the chi from there. So chi is equal to N sub I, 0.189 moles, divided by N total, 0.9582 moles. So we take 0.189 divided by our total to get a mole fraction of 0.19724. With sig figs, this would come out to 0.197. And that is the mole fraction. There are no units on it. If we wanted to double check our work, we can find the mole fractions for both nitrogen and carbon dioxide and make sure that all of those chi's add up together, which is totally fine. You can do that if you want, or you can just trust that you know what you're doing at this point, and that as long as you're showing that you added up all of those moles and did the part over the whole, that you got the problem correct. Okay, so here's one where we can use our mole fractions to find the individual pieces. So, we want to know the partial pressure of carbon dioxide in a gas mixture that contains 4.10 moles of oxygen, 2.38 moles of nitrogen, and 0.917 moles of carbon dioxide, and has a total pressure of 2.89 atm. So we want to find the partial pressure of this. Okay, so this is P total. And we want to find the partial pressure, PI. Spell total right. So we want to use this equation here. Because I want to find PI, I know P total, I just need to find a fraction. Now chi, we said, can either be a mole fraction or a pressure fraction. I don't have any pressures given here, or pressures that would allow me to find a pressure fraction, but what I do have is mole fractions, and mole fractions are equal to pressure fractions. So if we know the mole fraction, we can find that is the pressure fraction. So we'll go about finding N total and N and chi for the moles, and then use that to find the partial pressure. So our N total is going to be 4.10 plus 2.38 plus 0.917. So you have 4.1 plus 2.38 plus 0.917. So our N total is 7.397 moles. Chi, our mole fraction, is now going to be the part over the whole, and in this case it's going to be CO2. So 0.917 moles of CO2 make up the total 7.397 moles. And we get a mole fraction of 917 divided by 7.397. We get a mole fraction of 0.12397. Okay, so we have chi, we have P total. We can now take chi, 0.12397, multiply it, not even going to show an x, I'm just going to show it in parentheses, multiply it by 2.89 ATM. So we do that times 2.89. We get the partial pressure of CO2 to be 0.358 ATM. So because the moles and the pressure are proportional to each other as long as temperature and volume are remaining constant and unchanged, we can use our mole fractions to help us find our partial pressures, because a mole fraction is equal to our partial pressure. They make up the same kind of ratio, whether you're looking at moles versus pressures. Let's try another one. A mixture of gases contains 0.3 moles of CH4, 0.25 moles of C2H6, and 0.29 moles of C3H8. The total pressure is 1.50 ATM. Calculate the partial pressures of all of the gases. So pause your video and try this problem. Find your mole fraction. Once you have your mole fraction, use that to find the individual partial pressures. The first step that you're going to want to do is find your total moles. So N total is going to be equal to 0.31 plus 0.25 plus 0.29. So we get 0.85 moles total. So now we're going to take those chi values. I'm going to simplify this and just put it right in my equation instead of solving for them individually. We're going to find chi, multiply it by the total pressure of 1.5, and that will give us the partial pressure. So for pressure of, let's do CH4 first. We get a chi of, let's see, 0.31 divided by 0.85. which we're going to multiply by the total pressure, 1.5. So I just kind of simplified what I did in my previous example. This is chi. So we take 0.31 divided by 0.85 and then multiply that by 1.5. So that would give me a partial pressure of, for CH4 of 0.55 atm. Next up, we'll do the same thing for C2H6, except now its partial is going to be 0.25 over 0.85, but we're still multiplying that by the total pressure of 1.5. 0.25 divided by 0.85 multiplied by 1.5. We get 0.44 atm. And finally, we have the partial pressure of C3H8, and that's going to be equal to 0.29 divided by 0.85, which will be multiplied by the total pressure. 0.29 divided by 0.85 multiplied by 1.5, and we get a partial pressure of 0.51 atm. Now we can add these up and just double check our work. 0.55 plus 0.44 plus 0.51, and we get a total pressure of 1.5. So we can use our mole fractions to find our partial pressures. Here's one from your ALEKS homework. N2 gas is mixed with oxygen gas, and the sketch below shows a representation sample of the mixture. The total pressure of the mixture is measured and found to be 1200 torr. Calculate the mole fraction and the partial pressure of each gas in this mixture, and round your answers to 4 significant figures. Okay, so the way that we're going to go about this is still going to be the same. We're going to find the mole fractions and use that to find the partial pressure. But we can use our concept that molecules are proportional to moles in order to do this. So if we know the number of molecules total, and we know the number of individual molecules, we can find the chi, the mole rate, the mole fraction, okay? Because molecules and moles are interchangeable. So let's count up our total molecules. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 molecules total. So that's going to be our denominator in each of these. Nitrogen is blue. So nitrogen, how many molecules of those 20 are made up of nitrogen? 1, 2, 3, 4, 5. So nitrogen's mole fraction is going to be 5 over 20. And your ALEKS homework wants you to find the decimal for this, so we are going to do 5 divided by 20. So 0.25. For oxygen, oxygen is red, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oxygen, there's 15 out of 20. So we do 15 out of 20, and that's 0.75. So those are your mole fractions. 0.25, and 0.75 for each of those. Now we can use those mole fractions to find the partial pressure. We know our P total is equal to 1200 torr. So for nitrogen, we're going to take 0.25 and multiply it by 1200. So the partial pressure with respect to nitrogen is 300 torr. And for oxygen, we'll do the same thing, but use 0.75 as its mole fraction times 1200. So its partial pressure is 900. We can add these up. This adds to 1200, check. And we can add these up. They come to 1, check. So we know we did both of those correctly. So when you see this on your ALEKS homework, that's what you need to do. Make sure that you are equating molecules and moles together.